We have seen that pressure at a point is same in all directions, but at different points the pressure will be different. Let us see here. There is fluid, and in the last video we have seen that if you consider a particular point, and at this point the pressure will be same in all directions. Here let us say P1, and here also there will be P1, 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 P1. And if you consider a point deeper inside the fluid, at this point, here there will be P2, here there will be P2, and here there will be P2, and here it is P2. Here P2 is greater than P1. This is why is it greater than P1? We will see now. And also remember that in a horizontal plane, let us say in this plane a point is there here. Here also there will be P1, 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 P1. But as we go into deep into the fluid, the pressure increases. Let us consider a point, and the element of this point is, let us say this is the element, and this is not a point, this is the fluid element. So here the pressure forces for a fluid element, two types of forces will be acting. One is pressure forces from all sides, of the adjacent particles, and another one is weight of the particle. So these both are the forces that will be acting. These are the pressure forces. And these pressure forces will be acting on the surfaces, and also there will be weight of the fluid element that will be acting downwards. So here these are balanced. Let us say this is Fx and this is Fx. These both are balanced, and this is let us say Fy, and this is Fy, and this is Fz, and this is Fz1, this is Fz2. These both are not balanced because there is weight acting downwards. So these are all balanced, Fz, Fx and Fy. So this is X, this is Z, and this is Y. So X and Y are balanced, so we don't need to bother about it. And we have unbalanced one, which is Fz1 plus W is equal to Fz2. So here if we see that the force acting on the top surface is Fz1 and on the bottom surface is Fz2. So here, due to this weight, there will be increasing pressure from the downside. If you consider this in 2D, the pressure forces acting on the top side, let us say this is the pressure forces on the top side is P1, and there will be increase in pressure on the sides as the depth increases. And here, due to this weight acting downwards, there should be resultant increase in pressure from the downwards. Should compensate the weight of the fluid, so there will be P2. This is P2. And now, if there is a derivation of this equation, if you want it, you can refer SK Songbook. I am not drawing it. So this will be dP by dz is equal to minus W. What is it indicating is that as Z increases, the pressure is decreasing. Here there is negative sign. As Z increases, if we go on top from the bottom, this is Z direction, right? As we go, as we elevate, the pressure acting will be decreasing. This minus sign is indicating that. So this dP by dz is equal to minus W, and this W is specific weight. This is specific weight. And also we need to remember that this is very important equation. This is very important, and this can be applied for incompressible and compressible as well. It can be applied for compressible and incompressible fluids. So for liquids, the density will be almost constant. So dP is equal to minus rho g into dz. So we can write this W as rho into g. Specific weight can be written as product of density and acceleration due to gravity. So for liquids, rho is equal to constant, mostly constant. So P integral of dP is equal to minus integral rho g dz. So rho and g are constant, so P is equal to minus rho g into z2 minus z1. And here we have considered this point, right? Let us say this is the datum. This is okay, z1. So this is z2. This is z1. P is equal to rho g into z1 minus z2. Let us say z1 minus z2 is equal to h. So P can be written as rho g into h. So what is the h? This h is height from free surface. So if this is the fluid, and we have considered a point here, and this is the rigid surface on which fluid is resting, and this is Z2, this is Z1. And this is H. This is the free surface of fluid. So P is equal to rho g H. But in oceans or seas, there will be much deeper one. So as we go deep into this, the total weight on the fluid layers will be increasing. That's why the pressure will be increasing. That's what we have seen here. But in oceans, due to this very high pressures, the downside layers are more compressed, and due to this, the density will be more in the downside layers. So in that case, we use dP is equal to minus integral rho g dz. And here rho is not constant in case of this one, which means as the rho increases as we go deep into the ocean. So with z, rho also increases. In that case, rho is not a constant one. And in case of gases, we do not consider the effect of this variation of pressure with depth. So if there is a container and there is a gas here, pressure will be exerting in all directions. But we have seen that pressure in the deeper side will be more. But for gases, this rho is very low. Density of the gas is very low, and so this pressure will be negligible. There will be negligible pressure difference at different heights. So if I say on this pressure on the top surface is, let us say, 1 bar, and pressure on the bottom surface by applying this rho g h will be 1.00005 bar. If this is some 5 meter, this will be 1.005 bar. So this is a very negligible pressure difference. So we do not consider rho g h in case of gases, but in liquids this will be compulsory applied. And also how the pressure is distributed in this. Let us see that how pressure varies with the depth. We'll see now. There is a container and there is liquid in this. This is the free surface of the liquid. Here there will be atmospheric pressure acting, and also I forgot to tell this. Here I have taken P it is not actually P. Here it is P2 minus P1, integral 1 to 2. So here there will be P1 minus P2. Here the pressure is P1 and here the pressure is P2. So here, it is P2 minus P1 only. P2 minus P1. P2 minus P1. But if we see here, this P1 will be P atmospheric pressure and the P2 will be the actual pressure. So this P2 is absolute one. And if we neglect this P atmospheric pressure, this will be gauge pressure. This is gauge pressure. So P2 minus P1 is equal to P, and this is the gauge pressure and this is the absolute one. So we have seen that here there is a atmospheric pressure. So here there is atmospheric pressure, and let us say this is the amount of pressure. And as we go deep into this, so here we have seen that P is equal to WH or P is equal to rho GH. So P is directly proportional to H as a rho, if we consider rho and G as constant. So P is directly proportional to H. As we go deep into this, the pressure will be increasing. So this will be the pressure distribution inside this depth. And also there will be atmospheric pressure acting outside on the other side of the container. This will be atmospheric. This is also the atmospheric pressure. And if we, the resultant one will be the resultant pressure distribution will be like this. This is the resultant pressure distribution. So finally remember this: dP divided by dz, dP by dz is equal to minus W, which is equal to minus rho G. So this is valid for compressible and also incompressible and incompressible fluids. For both it can be valid. And P is equal to rho GH or WH. This is valid for incompressible fluids. So remember this. This is very, 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 very important. P is equal to rho GH, and we will be using this equation in calculation of pressure in manometers. So that's it for this video.